In today's lesson, we're going to look at the different notations that we have in calculus to be able to find our derivative. Now, we've been dealing with something that we know quite well. We know that f dash x, which is the derivative of the function of x, with respect to x, is equal to, this ends up becoming 10x plus 3. So that's easy enough, okay? But let's go see if we are if we have been giving it, if we have been given it in a different format. Instead of being given as fx, we are now given it as y, or we've got a dx of a function and we've got a d over dx of a function. Let's go see what that is. So if I've been given it as y, and I've been given the function y is equal to 5x squared plus 3x. The way that I deal with writing this function is I cannot write fx. I have to write the derivative of my function y with respect to x is going to equal to, and we now apply our derivative rule. And we sit there and we say, okay, well, we know that that ends up becoming, we do the derivative rule like we would normally do. Take the 2 times it in front, minus 1 from it. Okay, so it becomes 10x plus 3. That's easy enough, hey? If it's been given as a y, we have to write dy over dx. That is how you write it. That is the rule. If I give you it as fx, you can write f dash x. If I give it to you as y, you have to write dy over dx. Okay? Over here, we've been given the derivative of the function in the form of dx open bracket function. So if we write this out, let's write this how we would see it. We'd be given d subscript x, and they would put my function in here. I've got 5x squared plus 3x, and it's in square brackets. That's important. So how do I solve for the derivative of it? Well, all I do is I write equals, and I drop all this nonsense around it, and I apply the derivative rules to that, which ends up being 10x plus 3. Once I've simplified this, I can then write it as that. We're going to do a couple of examples, you'll see. Okay, and here I've got, they're asking me to find the derivative of the function with respect to x. But in this case, I haven't been given the function in this formula, so all I do is, this is what it would look like, d over dx, and I put the function in this bracket, which ends up being 5x squared plus 3x. That's my function. And I keep that function and I write equals to it. If I can simplify it straight away, and I can, it ends up being, or I can derive it straight away, ends up being 10x plus 3. So it's just the different notations. We're going to move on to a couple of examples so that you can see exactly how we apply these notations in various types of examples. Example 1, determine the derivative of y with respect to x if y is equal to 2x plus 1, x minus 3. Now remember, we don't have a rule, there is no rule for multiplication to do can I just write for timesing? I'm running out of space here. There is no rule for multiplication when we're dealing with derivatives. So I can't derive that yet. I first have to simplify it. So then I go, right, y is equal to 2x plus 1, x minus 3. I multiply the first with the first, so it becomes 2x squared. Multiply the nose and the mouth, so x minus 6x ends up becoming minus 5x. And I end up multiplying that, which becomes minus 3. Now I have it in its simplest form, right? Or in its trinomial form. And now I've got negative, so I use my negative rule. And once I apply the derivative, do I then write dy over dx? you do not apply the derivative. You do not write dy over dx until you find the derivative. And we are now finding the derivative. We take the 2 times by 2, becomes 4x minus 5. And that is my answer. Only write that value down when you're finding your derivative. Okay. Here you've been given determine the derivative of this function with respect to t. So we keep the dt until we have simplified this value. So we've got t squared plus 5t plus 6 all over t plus 2. I need to simplify this first. So I keep the dt, keep everything in a bracket. I can factorize my trinomial. I end up finding the factors of my first, t times t. What sign am I going to have in each bracket? Well, this sign tells me I'm going to have the same sign in each bracket. What sign am I going to have? I look at this sign and that tells me I'm going to have a plus in each bracket. And then my factors of 6 is 6 and 1 and 2 and 3. Now, guys, if I'm going to have a plus in each bracket, which one gives me a 5 in the middle? 6 plus 1 is going to give me 7, so that's not going to work. 2 plus 3 ends up giving my factor in the middle, right? So, or my term in the middle. So we end up using 2 and 3, and we end up putting that over t plus 2. We close our bracket. Now we can simplify. So here we can take that t plus 2 divides into itself once and into that one once as well. And then we end up having our simplified dt form, which is t plus 3. I still have not differentiated. Once I've derived, I found my derivative, once I've done the differentiation, I can drop this dt. So now we end up solving for this. We know that when we have a constant, that becomes a big fat 0, and we've got an invisible 1 here. We're going to times it with what's in front, and we're going to minus 1 from that. That ends up giving me an answer of 1. So there I found the derivative of it. First I had to simplify it before I could actually apply the derivative. Once I've applied the derivative rules, then I can drop that function, that notation. Okay. Example 3, determine the derivative of this function with respect to x if we've been given the function 12 of the cube root of x plus 1 over 2x plus 2. Now, let's do a little bit of scribbles here. We know that we are not allowed to have our x's in the denominators. We have to bring it up to become a numerator. And this, we know, according to our surds rule, this is the same as going x to a third, right? Because it's got an exponent 1 here and you divide by the root on the outside. So let's try and simplify this down before we actually apply the derivative. And only when we apply the derivative do we drop this value. So we write it as d over dx. And we keep our square brackets. Let's write this in a notation that we can deal with. Bring all our x's around and sort them out, right? This becomes x to the third plus 1 over 2. And we brought the x up, which becomes an x to the minus 1. It's got an invisible 1 there, plus 2. Okay, now we apply our rules. We know that this is our constant. It becomes a big fat 0. We're going to take whatever is at the top there as an exponent, times it in front, and minus 1 from it. And over here, we're going to take this, times it with what's in front, and minus 1 from it. So that is when we start applying the derivative rule. And once I apply the derivative rule, we drop this notation. So I've now applied the derivative rule. I'm going to go a third times by 12 x 1 over 3 minus, remember 1 can be written as 3 over 3, plus, what are we timesing it with? Minus 1 We're timesing a half with minus 1. We end up having x minus 1 minus 1. And all plus 0 because we've applied our derivative rule. Now we can simplify this. We end up knowing that this 12 is also written as 12 over 1. And because of that, we can now simplify. 3 can go into itself once, and it can go into 12 4 times. So we can write this as 1 times 4 is just 4. X 1 over 3 minus 3 over 3. 1 minus 3 gives me minus 2 over 3. And here we end up having a minus 1 times a half, which leaves me with minus a half. And minus 1 gives me x to the minus 2. I can rewrite this so that I don't have negative exponents. This whole thing goes down to the bottom. We have 4 at the top, and we have x to the 2 over 3 minus 1 over 2. This is a minus 2, so when I move it down to the bottom, it becomes a positive 2. I can simplify this even further. Instead of leaving it as a rational root, I can change it to square root. So we end up having 4 over the cube root, because that's the cube part, x squared minus, that's not right, I need to write a 1 there, 1 over 2x squared. So it was quite an ugly one. I think they like to put these types of ones in the test, but because we were focusing on the notation, I want you to remember, direct yourself to the notation. We want to find the derivative of this function with respect to x. So there is my function. Apply your derivative rules, and once you start applying your derivative rules, drop that derivative notation.